Hey everyone, and welcome to this explainer, made by Forge College. Go ahead and grab your magnifying glass and, maybe your favorite trench coat, because today, we are acting as smart contract detectives. We're going to demystify some major mapping limitations. Now, this builds directly on our previous lesson about nested mappings and key hashing. In that session, we learned how to model two-dimensional relationships without using arrays, which, as you know, is absolutely incredibly powerful for lookup complexity. But the very things that make mappings so efficient, like that constant time access and sparse storage, well, they can also create this sort of shadowy underworld of subtle, silent bugs when you actually try to write or update your data. So today, we're going to shine a massive spotlight right on those shadows. Okay, so here's our investigation agenda for today. First step, the mapping mystery. Then, the case of the lost update. Third, ghosts in the code. Fourth, the debugging playbook. And we'll wrap it all up with safe mapping blueprints. Let's dive in. Section 1, the mapping mystery, investigating missing data on the blockchain. You see, mappings are a bit of a double-edged sword. They won't usually crash your code. Instead, they'll just quietly lose your data. Honestly, it's the perfect crime. Let's open up our first investigation. The case of the lost update. Imagine a user pays their gas and registers their name as Alice on your contract. The transaction succeeds. Everything looks great. But when you check the ledger, it's completely blank. Poof, gone. So where on earth did the struct data go? Well, to solve a crime, you gotta recreate it, right? If we follow our manual reproduction steps in a local environment, like Remix for example, we can observe this exact behavior. Step 1, we call the register function with the string Alice. Step 2, we read the state of our contract by calling the user's mapping for account A. And then, step 3, we clearly observe the symptom. The name field is just an empty string and the ID is 0. Our updates simply did not persist. We went through all the motions of updating the blockchain, but absolutely nothing stuck. So the culprit here actually comes down to one single, easily overlooked keyword, and it brilliantly illustrates a fundamental core concept in Solidity, which is memory. Memory is basically just a temporary execution space. Think of it like writing a legally binding contract on a paper napkin while you're sitting at a coffee shop, and then just tossing that napkin in the trash on your way out the door. If you retrieve a user mapping from the blockchain and assign it to a memory variable, you are strictly working on a temporary copy. Any changes you make to that copy, they get thrown right out the moment the function finishes executing. The good news is the fix is incredibly simple. In our buggy code, defining user memory U gave us that temporary napkin. But by changing that single keyword to user storage U in our fixed code, we create a direct reference to the actual mapping slot on the blockchain. We are no longer working on a disposable copy, we are writing directly to the permanent ledger, ensuring your updates are literally carved in stone. Boom! Case closed on the lost update. Moving right along to section 2, ghosts in the code. The mystery of the unregistered user. Okay, so imagine your contract has a function called isRegistered. Suddenly, your contract claims an address is fully active, even though they've literally never interacted with you. If we take a completely unused address, like address 0 for instance, and pass it in, our buggy code actually returns true. It's falsely identifying a phantom user. And think about it. If you're relying on this check to grant permissions or send funds, your smart contract is essentially just swinging the vault door wide open for a ghost. Not good. To understand why this happens, we need to look at another mechanical reality of Solidity: default values. In most programming languages, right, if you ask a hash map for a key that doesn't exist, it throws an error, or maybe returns null. But Solidity mappings, they do not throw an error from missing keys. Instead, they hand back a default value. So for an integer, it hands back a 0. For a string, an empty string. For a Boolean, false. This quirk effectively creates a massive parallel universe of infinite blank users. So if you're checking if an ID does not equal 0 to verify existence, well, you've fallen right into the trap. Why? Because an actual legitimate user might be the very first person to register on your platform, meaning they legitimately have an ID of 0. We banish this ghost by using the fixed code approach, a dedicated Boolean flog, like .active. This gives you a single explicit source of truth. When a user registers, it's true. If they're deleted, it's false. Just like that, no more ghosts. All right, section 3, the debugging playbook. Well, we'll look at structuring our investigation. Any good detective, and for that matter, any good developer, documents their findings.
This debugging table is a fantastic little blueprint to keep right on your desk to turn all that debugging chaos into a totally systematic process. It maps frustrating symptoms right back to their mechanical realities. So, see empty fields? Well, your root cause is probably a memory copy, and your fix is using a storage reference. Seeing false positives? Your root cause is likely numeric defaults, and your fix is a Boolean flag. It's just a perfect one-to-one translation from symptom straight to syntax.
And that brings us to Section 4, Safe Mapping Blueprints. These are our core design principles for Solidity.
Let's wrap things up by distilling all this detective work into core design principles. Basically, the fundamental laws of physics for Solidity mappings. Rule number 1, always use explicit Boolean flags to check for existence. Number 2, always use storage references when updating nested structs so your changes actually persist. And number 3, just a hard structural reality to accept, mappings are not iterable. If you ever need to count or list entries, you're going to need to design a parallel array to keep track of those keys. Now you have these incredibly robust debugging tools securely fastened right there in your developer utility belt. You know exactly how to safely read from nested mappings, and now you know how to safely write and update them without falling into those super common memory or default value traps. So are you ready to design multi-structure contracts? Thank you so much for joining this explainer made by Forge College. To review your debug reports, dive deeper into this topic, and just continue your Web3 journey, definitely head over and visit forge.college. As you close this case file today, I want you to ask yourself a final question. How will you combine these safe mappings with other complex data structures to build your next major decentralized app? Keep your syntax sharp, keep building, and until next time, case closed.